Welcome back, everybody. This is our final lesson for Unit 3 on earthquakes, volcanoes, and plate tectonics. So today's lesson, we're going to learn a little bit about volcanoes. I know that one of my classes, I showed you a really interesting volcano on Maurice and Katja Craft. The rest of the classes, you guys didn't see that. Perhaps if we have some time later on this week, we can watch that. First of all, volcanoes, how do they form? Well, we've kind of been learning about this a little bit throughout the unit, especially when we were covering plate boundaries. But molten rock within the earth, you guys know this stuff, called magma, along with gases, when it rises up through the cracks and weak spots in the crust, it forms volcanoes. And when this molten material with gases from inside the earth break through the surface, it flows outside and then is called lava. So where do volcanoes form? Well, we already learned this stuff, but it's good to review. First, at islands and mountains formed by subduction zones. That's that, remember, the hot rock is melting back up from underneath as the one plate subducts underneath the other. And that hot rock, it does erupt as either volcanic island arcs or as volcanic mountain ranges. Second, along those mid-ocean ridges, there's lots of magma coming up through the Earth's crust there. And third, at hot spots, which are kind of a new thing we haven't really discussed much about. These are kind of like weaker points in the crust. We don't really know why the hot spots are there, but they are located down inside the Earth underneath the crust in the asthenosphere. And these weak points in the crust are located over unusually high heat flow in the mantle. The crust may move on top of those hot spots and create more islands, which we'll see. Some examples. See if we can get that to show up. Hawaiian Islands, they're a hot spot. The Hawaiian Islands, kind of like, the hot spot staying in the same spot, but the Pacific Plate, as we'll see, is moving over the hot spot and it's creating a new island in the chain every so often. We're talking on the scale of millions of years, though, not like every year there's a new island. So here's that first example, volcanoes at subduction zones. So the Andes Mountains, right along the coast here, they are volcanic. Not every single mountain, obviously, but there are volcanoes in those mountains. And that's created because the Nazca Plate is subducting underneath the South American plate. And as it does so, it melts, and the melted rock comes up in the form of volcanoes. Okay, we also have volcanoes at mid-ocean ridges. So here's the mid-ocean ridge, the Mid-Atlantic Ridge, running underneath the Atlantic Ocean. And remember from our side views from back in the part of this unit when we learned about divergent plate boundaries, diverge, move apart, that brand new rock is coming up and kind of forcing the rock on the surface that's already there apart. But that brand new rock is coming up in the form of volcanoes in the bottom of the seafloor. If you look, there's a lot of mid-ocean ridges around the planet, so a lot of this volcanic action is actually underwater. There's probably just as many volcanoes underwater as there is on the surface of the Earth. Maybe more. All right, the next and last category where the volcanoes are found are at the hot spots. And you can see the Iceland hotspot here, the Canary Islands hotspot, the Helena hotspot, Bouvet hotspot. There's hotspots everywhere. The ones that are close to home for us, the Yellowstone hotspot, which is actually underneath the land. And that's what is responsible for giving Yellowstone all its great geysers and paint pots. And the Hawaiian hotspot, because it's on a state of the United States, Hawaii. And that's what has created the Hawaiian Islands. The whole chain of Hawaii is a hotspot. And there's others too, the Tasman hotspot, for instance. So those are the three places, the three ways and places where volcanoes can form on the Earth. We have our subduction zones, our mid-ocean ridges, and our hotspots. Okay, now let's discuss three types of lava. That's right, Coca-Cola and a vanilla milkshake. No, I show you this because it's a kind of analogy that does help you to understand different viscosities of lava. Basaltic lava, for instance, made from seafloor ocean crust, when it's hot, when it's liquefied, it's very fluid. It melts between 1,000 to 1,200 degrees Celsius and is silica poor, which means it doesn't have a lot of silica in it. It's not very felsic, obviously, and that's why the dark Coca-Cola helps you remind you of that, because you learn that basalt is a dark colored igneous rock, and Coca-Cola is kind of fluid. You know, it's very easily spilled, runs out everywhere. And that's the way this lava acts. There's some photographs in my classroom of Hawaiian eruptions, and you can see the very fluid lava. Now, rhyolitic lava is much thicker. It's silica rich, which means it's more felsic in composition. It has a lot more ingredients that make it kind of gooey instead of runny. And andesitic is a mix between the two types that I've just mentioned. Sometimes these andesitic lavas are the most dangerous kind, because we'll see they create some pretty big volcanoes with some really dangerous eruptions.